I guess we'll get started. We're recording this webinar for posterity. This MicroObservatory, second in our series of monthly MicroObservatory Mondays, where we want to give some more background on MicroObservatory, some more ideas for projects for you to implement with your students, especially for our veterans of the YouthAstroNet program as you're looking for deepening your own knowledge of what can be done through YouthAstroNet and what you can engage your students with. So today's agenda, I wanted to talk a little bit more about some astronomy projects, some ways you can investigate astronomy content with microobservatory images. I know a lot of you have kind of started with the astrophotography art and science, or poetry and science, but we're going to investigate a few things. Some new features of the software that have come up since you may have done your first training, and I want to make sure you're aware of those. And then we'll end with a little tutorial on how to get the best results from an RGB image, and some Q&A. So anytime you have questions during the presentation, feel free to type them in the chat box. Welcome to Jeff. Nice to see you here. And we're just starting now, and the agenda is on the screen. So, I know a lot of you have, almost all students on YouthAstroNet. In fact, the most requested image from our microobservatory telescopes is the moon, and it's a great image to request because it changes every night, and there's a lot of investigations that you can do with moon images. So I wanted to just actually bring some moon images into the into view here and talk about some of the investigations that you can do. On the left side of the slide here, these are actually Galileo's drawings. Before there were cameras or CCD detectors attached to telescopes, there were eyeballs. And Galileo's was one of the first eyeball detectors attached to a telescope. And these are the data that he collected, and students can do the same. So I'm going to bring in my YouthAstroNet portal into view here, and open up JS9. And I'm going to see if in my list I have any moon images. I think my most recent moon ones, let's see what that looks like. Oh, was a cloudy night. All right, so I'll close that right up and open up an archived image. Of this moon, and I'm going to open another archived image. So I have two moons open at once of this image. And you can see that I have a third quarter waning third quarter moon here, and then the other one is the full moon. And so in terms of projects or questions you can ask of the moon and students can do, obviously they can take images of the moon over a sequence and create a moon calendar, or there's a interesting tool in JS9 that you should be aware of called blinking, which allows you to take a number of images that you've loaded into JS9 and blink from one to the next to the next to the next sequentially, so that you can see change over time. And if I take these two images of the moon I have in here, you can see, and I click on them both and I blink them, then my JS9 window is going to blink between them. Now, this isn't very helpful when the two phases are so far apart, the full moon and the third quarter about 3 weeks apart, but if you have a number of images, and I'm going to stop blinking them, And note that you can also use the, do we have that in there? Blending, okay. Image blending to see both images at the same time. And so typically you want to do this using the screen mode. So blend, I'll click that one using screen. Right? And you can see I have two of them here. And one thing you can notice right away is the moon appears a completely different size in these two images. I'm going to use my shift tool, right, under shift I'm shifting that smaller moon. You can see it down. And you can see that it's definitely, and I'm going to shift it over so that it's kind of on that left edge. There we go. And now I'm going to take off image blending and do my blink again and see if we can note that difference between the two images even more. So I'm going to turn off image blending, turn on blinking. Right. So another thing I'm noticing is this crater kind of wraps around a little bit. There's one thing that happens with the moon across its phases is that we usually think of the moon, the same side always faces us, and that's true, but actually a little bit of the moon on the right and a little bit on the left, depending on exactly where we are in the phase, you get to see around the side a little bit more than you do at other phases. And so all these things can be investigated by exploring many images of the moon. I'm going to stop that blinking right now and show you one other investigation you can do with the moon, which is around the size, and we're going to explore size and scale a little bit more later as well. But we just noticed that these two images of the moon, one from the September 28th, if you look over here on the screen, right, the image file tells you exactly when that moon was taken. So the moon that's on the screen was in 2015, September 28th, and it was quite large, whereas the other image of the moon was from January 2nd, here it is here, January 2nd, 2016, and the moon was small. Does anybody have any guesses in the chat box as to why the moon might have changed size between those two times, September of 2015 and January of 2016? Any guesses about what is going on? Why is the moon a different size in the MicroObservatory camera? Moon distance varies based on its orbit. Exactly, exactly. So the moon is sometimes a little closer to the Earth, and so it's a little bigger, and sometimes a little farther. And you can actually calculate that or measure the amount of difference between two different distances based on the diameter of the moon. And remember, you can make measurements, because the thing about microobservatory images is they are data. Images are not just pictures. And so if I use a circle tool and I try and get my circle to kind of match the size of my moon, that looks about right. Could be a little bigger, I think. Oh. Yeah, that looks right about right. And then I do region stats for that region. It wants you to click in the region. So here, my moon, the diameter of my moon is 342 pixels. And so we know, if you know the actual diameter of the moon, which is about 2,000 miles, it's about give or take. I'm sure I could look up the exact diameter, but so at this time the apparent size was 342 pixels, and in that other image in 2015, the full moon. Let's make a circle here. So we had, what was that, 342 pixels. And in this one, looks like we have a little smaller, 393 pixels. So from 342 to 393. And so clearly, this moon was quite a bit closer. And to get a just kind of an estimate of the amount closer, it's about 50 pixels over 360. It's about 1/6. It's 10, anyway, between 10 and 15% closer. So a fair, am I right about that? Have I got that right? Yeah, I think so. So you can actually calculate how much difference the distance is based on size. So those are some of the mathematical projects you can do. You could also calculate the sizes of particular features in this image. So if I know that the diameter of the moon is 393 pixels, and then I make another region, and I want to know how big is this Maria, this one right here, right? And that's 65 pixels. Then 65 over 393 equals X over 2,000 miles. And I can figure out the size of this Maria. So there's lots of investigations around how big things are over time that you can do. All right. So that's one way of using JS9. Let me look to our next investigation. Moons of Jupiter. So here's another change over time object. And I'm going to actually bring my JS9 back into view for moons of Jupiter. And Jupiter actually isn't up currently in this season. We're going to have to wait until a few months from now before it's back in the sky when you can observe it. But I wanted to show you another feature that just became available recently, where you can look in the MicroObservatory archives to find images of objects that your students want to investigate. And there's a really easy way for them to get them into their JS9 window. So what we're going to do is go back, actually back to the main page. We have not actually put a link to the archives that have everybody's images, everyone, not only YouthAstroNet observers, but all the observers who use MicroObservatory. There's a link to a archive, and the way you find that, we'll put a link right on here for students. I think we'll put it right either in the robotic tools. One way to find that is if I make another window here, and we just type in MicroObservatory, and you get to the main page where you have a link to your YouthAstroNet portal. You'll see right next to the YouthAstroNet portal link, Recent Image Directory. So I'm going to click on Recent Image Directory. And here I have all the images that anybody has taken over the last 30 days. But then at the top, this is the key resource that will create a link to our image archive. And here, click on that. We have all these categories of images. So if you want to investigate the moon, we have images of the moon from this year, from last year, going back in time. And so you can, if you didn't have time to take images of the moon for a whole month, you can investigate that. Or if I go back and I wanted to investigate moons of Jupiter, and Jupiter isn't up this season. So I'm going to go into the Jupiter archive, and I want to look for a bunch of Jupiters taken on the same night. And I see a bunch right here. I see a bunch right here taken on July 8th. Ooh, way back in 2009. This may not work. I'm going to have to see whether our FITS files are of the right. Let's find out. I'm going to open my JS9 tool, and I'm going to drag that Jupiter image. Actually, I need to get the, sorry. I need to get the, not the GIF image, but the FITS image. So I click on that, and here is that MicroObservatory image of Jupiter, and you can see that Jupiter is overexposed so that you can see the moons here. I'm going to drag and drop that FITS image right here onto the JS9 window. Drag, and it plus and drop. Ah, yeah. FITS files from 2009. We had an illegal character in the file that came back from the telescope that JS9 doesn't recognize. So make sure you're not using really old images when you go to the archive. I guess I'm not going to be able to show our Jupiter's moon sequence here, but I will show you these three images in MicroObservatory. You can see 3 moons right here. If I click on the next image, you can see that 3rd moon has gotten a little, this is an hour later, it's gotten a little closer. Actually, an hour earlier, I think. Yeah, we're going back in time, 07. And now you have a moon peeking out of the, I don't know if, can you see this on your screen? It's right. You can see there's 4 moons visible now. So the moons every hour move. And so you can see that movement by comparing multiple Jupiter images. So motion over time is another investigation that can be done. And it's another one that Galileo himself did, and realized that there were satellites going around Jupiter. The first to, this is one of the pieces of evidence that Earth was not at the center of the universe, because there were things going around Jupiter. The sun is also a great object to investigate over time. And right now, there are occasionally sunspots on solar images, but the sun is quiet. But a recent event that I think many of you probably participated in was the eclipse. And we do have an archive of MicroObservatory images that were taken this past August, August 21st. And I want to show you how you can explore those in JS9. So I'm going to bring, again, my YouthAstroNet portal into view. And the solar archive, Erica happens to have posted a news post about it in the news forum. And so I'm going to find that right now. Solar Eclipse 2017 images. And she has a link right to those images. And she's telling you how, right here, how to drag and drop like we just did. So I'm going to click on the link she provides in that post. Click. Okay, and you'll see these are all the images of the Great American Eclipse of August 21st. And one thing you can notice is we were taking that with both telescopes. Frank was Arizona, Massachusetts, 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 Arizona, Arizona, Massachusetts, Massachusetts. So you may want to compare images of one place to another, or you may want to have your students follow the eclipse in one place. And you can sort on the MicroObservatory image archive by telescope, which will also end up sorting by location. Or you can just compare one with the next. So let's try that. I'm going to get right in the middle of the eclipse down here, and I'm going to compare Arizona image with these two images here, Arizona and MicroObservatory, taken at the same time in universal time. Okay, wasn't the same time in both. I don't know if it was 1702 universal time. I guess it was about 2 in the afternoon here and about 11 in the morning in Arizona. So let's oops, let me find, there we are. Let's get our JS9 and those eclipse images, and now we can practice our drag and drop. So remember, I click on the file I'm interested in. Oh my. That looks like a total eclipse. Something strange happened there. I might, oh, okay. Just touching. I think I want something where I see a little more happening. So let me look here, see if I can find something. Ah, we have a lot from before. Let's see, let's find a little later. Is this working? There, that looks better. So there's Arizona eclipse, and I'm going to do this drag and drop move. Drag and drop. Okay, and here you can even see there were some sunspots on eclipse day. Very nice. And now I'm going to find another image taken from Massachusetts at the same time. So there we go. So these look very different. And let's try that blinking again, that blink tool. And we'll blink between them. And remember, so this image was taken at August 21st, 1800 Universal Time. And the other image, also 1800 Universal Time, but from Arizona. So we're going to blink those images back and forth, right? And what's going on here? Any guesses on why do Arizona and Cambridge they're taking a picture at the same exact time? How come it looks so different? Any guesses in the chat box? Well, of course, here you had, remember that depending on where you were either going to see a partial eclipse or a total eclipse. And so here in Cambridge, we never got to see that moon cover the full disk of the sun. And neither did they get to see it in Arizona, but both locations were on either side. If you looked at a map of the United States, those locations are on either side of the path of totality. And so it's kind of like holding up your thumb against the image of me on the screen and opening and closing both eyes. One eye is Cambridge, the other eye is Arizona, and my thumb moves from one side to the other depending on the point of view. So that's something called parallax. And I'm going to stop this blinking because here we go. And you can even measure the difference in angle between well, that may be more math than I can describe at the moment. So between Cambridge and Arizona. So you could do a series of images from an animation. And in fact, one of our MicroObservatory observers actually did this blinking across 20 images of following that disk of the sun right across the path, disk of the moon right across the path of the sun. Okay, another investigation. Let's go back. And remember again that size and scale activity that we did at the beginning of the webinar with the moon at 2 different places in its orbit where it was close and far. You can do with many objects. And I wanted to point out in the curriculum, we actually have an activity where students use cameras or their smartphones or whatever to take images of objects and notice this idea that things that are farther away, if they're the same size, appear smaller. Things that are bigger, if they're farther away, can appear the same size. That's like the sun and the moon. And I wanted to just show you that that activity and show you some things you can do with that. So if we go again to our, we're going to go to our educator portal and look in the curriculum and look for distance, size, and scale. There's a couple of activities here. And I want to open up this one in particular. Have I got this right? Is this the right one? We'll find out. Was that it? Where did, no. All right. Which has students use a baseball, some 3 different balls, and take pictures of them to try and get them to appear the same size in a camera, kind of placing them on a table and taking a picture from the end of the table and checking their apparent sizes. Now we have an example of this. Where is that example, Erica? Can you read the image? Yeah, it's in the portal.
Go to the student portal.
We'll go to the student portal. And down to size and scale. That's right. And there's the image. So this image is of identically sized balls placed on a table and a picture taken of them. And so I want to show you how you can work with kids to understand this idea that the MicroObservatory camera looking at objects in space works the same way, since it's the same camera taking images of things as they appear closer or further change apparent diameter in the image. So I'm going to save this image on my page here. I'm going to save it on my desktop, colored balls chevron here. Okay, and I'm going to save it so it's right at the top. And I'm going to upload that image right into JS9. JS9 now allows you to upload JPEG images, but it does open them as black and white images, even if they're color. So you have to anyway, so we're going to open that colored balls chevron. I dropped it right here on my desktop. And there it is in JS9. And now we're going to figure out how much further from the camera on that tabletop. Remember, we had this image. So these balls are placed, here's the edge of the table. These balls are placed somewhere on this table. And I can make a circle region. Maybe I want to zoom so I get this a little better here. There we go. So I have my ball in the front. I'm going to do an analysis of region stats here. Actually, sorry, cover that up. Sorry, it's a circle. Get rid of that. Close. So my region stats show me that the diameter of my circle is 122 pixels. And we'll move my image over. And this ball is the same exact size, except that now it's about 80 pixels. So we had, what was that first one? 120 pixels, 80 pixels. And here is one that is 60 pixels. So can anyone guess the distance from the camera to the ball that is 60 pixels compared to the original ball in front that's 120 pixels? Is it 60 times further away? Any guesses in the chat box? 2 times, yeah, exactly. So these two objects, the same size, the one that's twice as far appears half the apparent diameter, and the activity in the curriculum actually has students try to guess from other students' pictures where they had them placed on the table. So it really helps understand this idea between size and distance. All right, so those are some investigations. Let's go back. Where am I? I've got so many windows open now, I've lost my slides. There we are, exploring the size of objects. The last thing I wanted to show you today was, and of course, for objects across the universe, for each of these, is that in our curriculum, the size and scale that shows? Not sure. Yeah. Well, so if you have a series of galaxies, for example, galaxies, if you assume they are about the same size, which would be a good first assumption, then students can measure the size of different galaxies, compare them to the Andromeda galaxy, which is 2 million light years away, and make an estimate of how far away some of those galaxies are, just like you could estimate that ball, how far away that is. So those are all examples of activities that can be done, investigations of real size and scale. Last thing I want to show you today is going back to JS9 and using RGB images. I'm going to get back in the portal, go back to the activity portal, and make sure some of you who may have been in our first cohort, we actually hadn't had JS9 ready for creating RGB images, and now it does it quite well. And so I wanted to give you a little tutorial in advanced RGB image making. So let me get into JS9. Okay. And remember, the telescope, I'm going to use this set of dumbbell images that are in the archived images here. And remember, when I open up the Dumbbell Nebula, which is a cloud of gas and dust, when you first open it up, I don't see a nebula in there. It's a very dim object. And for dim objects, there's a 3-step sequence that always helps bring out the best. The first is to kind of drag down the high brightness limit till you start to see a little more in the image. I see it there. I'm starting to see something right about here. I'm going to make this a little bigger so you can see it on your screen better. Oops, I did both zoomed in. Here, let me get, there we are. Okay, so I've started to see something. So first, drag down the high brightness limit. Second, use log scaling, which enhances the dimmest features without oversaturating, without over highlighting the bright parts of the image. So log scaling enhances the dimmest parts of the image, but of course, that includes the background sky. So to enhance the contrast, we have to find out what is the brightness value, the pixel value of that background sky. And as I wiggle my cursor around, I look down right here, and I see it's about 322. So I highlight and type right in the low brightness limit, 322, enter. And then my Dumbbell Nebula is really standing out, and I can tweak a little bit that low brightness limit. Just click on the edges until I get a contrast I like. I can play around with stretching or shifting. That looks pretty good. Remember, the telescope doesn't know, the telescope detector doesn't know that this is red light. It was taken through a red filter, but the detector only detects bright and dark. And so this is the red light coming through the red filter, and this is the part of the nebula that was glowing in red. So what we're doing by giving it a red color map is simply telling the computer, this is the image that was taken through the red filter. Then we're going to open the green filter, do our 3 steps, bring down the high brightness value. I start to see it there. Use the log scaling to enhance the really dim stuff. Oops, I've enhanced the dark sky. Find out the dark sky value, which looks to be about 318, 19, 20. Set the low brightness limit at that, 320, enter. And there's the green part. I want to tweak a little, maybe like this. Tweak a little here. That looks good to me. Tell the computer, this is the image of bright and dark that was taken through a green filter. And lastly, do the same for the blue. So I bring down the high brightness limit for the blue, hit log scaling, find that low brightness limit of 314, it looked to me, 314, enter, and there's the blue data. And I'm going to tell the computer that's blue. But now, to tell the software, I want you to add those 3 images together. The light that came from the part of the nebula that was emitting blue light, the light that came from the part of the nebula that was emitting red and got through the red filter, and add the data that came through the green filter from the part of the nebula that was emitting green. You press RGB mode, and there's all 3 images added together, but not aligned. So it looks like I want to bring, it looks like the green and the blue are pretty close together here. If I open a magnifier here, And I can be on any couple of stars, and it looks like green and blue are pretty close, but red has to come up. So I'm going to go to my red image, which was the first image I loaded. I'll highlight that one. And I know that that's the active one because the red bar is on the bottom. And I need to shift it up. So I look for the shift tool. And let's click, 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 click. As I click, 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 click. And unfortunately, the shift tool only moves at 1 pixel at a time. So you have to keep clicking to get that red. There we go. And if we look in the magnifier here, get those red stars to be right on top of the green. Maybe one over to the left. That's pretty good. And now, I kind of want to highlight, I see that there's some red on the outside of this nebula. I kind of want to highlight it a little more. So I'm gonna, ooh, there we go. I like that. That looks good. Now, at this point, there's a lot of noise in my image, and there's several techniques, several advanced imaging techniques for getting rid of noise. One of them is by doing it in the software, and that under these tools, image filters. These image filters are different than the physical filters that were the red, green, blue filters that you actually use on the telescope. These are kind of like Photoshop. They're like Instagram effects that help touch up your image. So you always want to do these last because they because you want to use the good data and enhance it as much as you can before you use these image filters. But what I always like to do, let's take a look at that image. I'm going to actually zoom in once because I want my dumbbell nebula to be highlighted. What I always like to do is first use the reduce noise filter. And see how that got rid of all, I don't know if you can see on your screen, it got rid of all the tiny little hot pixels. And then sharpen. So at first I kind of blur and reduce noise and then sharpen. And that gives me kind of what I like best about this RGB image. So I might want to, yeah, is there a question?
Oh, no, I was going to make a point.
Yep.
I'm not sure if they can hear me. So.
Oh, okay. Erica is
That those
wanted to
image
highlight.
filters have to be last.
Yeah.
If you continue to process.
Ah, thank you. Yeah. Erica pointed out something I neglected to mention. Another reason you have to do those image filters last is if I were to now go and say, oh, you know what? I want to bring down that high brightness limit on the red a little more. As soon as I start to do that, click once, all my processing disappears. So that noise is back that I just reduced. So you have to finish enhancing your image using the sliders and using the scaling. And the last thing you want to do is use these. So again, reduce noise. That gets rid of all that little pixely stuff. I could sharpen, or another image filter that often highlights the features of your object that you are interested in is Emboss. It actually makes it look like it's a piece of fabric. So I'm going to click on Emboss. Let's take a look at without it. Click on it. And it makes it three-dimensional. So you see the nebula sticking up above the background here. And you can see the central star right in the middle of this nebula. That's making all that. And you may or may not like this effect. If you don't like it, again, if you just click on any of the slider bars, you'll get rid of all the filter effects. And so That's the last thing you want to do. There is one other way of optimizing images in RGB, and I'm going to show you one black and white image where I do this. And that is to calibrate images by subtracting a dark image. And that's the last thing I'm going to show you today. Many of you may have noticed, and I will go, let's go back to the main page. Let's go in my images I requested. And over the weekend, the telescope failed, but here, last week, you may have noticed at the top of any image request day, you have these dark images from whatever telescopes were up that night, Ed, Ben, and Cecilia. And so those dark images are an image taken with the shutter closed for 60 seconds. Well, why would you want an image taken with the shutter closed? It turns out the detector itself, the heat from that night in Arizona, causes all those little hot pixels, causes noise in your image. And so what professional scientists often do is they subtract a dark image from their science image. So I'm going to find a science image of the Dumbbell Nebula here. Here's one that I took. I don't know how it came out. We'll find out. Well, not too bad. All right. So again, remember that I bring down the high brightness value. Here it is down here in this image. I log scale. And what's that last step? Background sky is about 440 in this image. See, so the darkest places in the image are about 440. So I'm going to set this at 440 and hit enter. Yeah, so this wasn't a great night. You can see it's kind of hazy, but there's my image. But what I'm going to do is open up the dark image from that night. And let's see, I guess I can, how can I do that? It's in my list, right? So I need to know, whoops, I need to know what telescope this dumbbell image was from, because that's the dark, you have to open up the dark image from the same telescope. And if you remember, I can find out by displaying my FITS header. That's that metadata with every image. It looks like this was Ed. So I need to open up the dark image from Ed, right here from that same night. And you notice it looks like a dark image, and it is a dark image. And as I put my cursor in it, you can see almost everywhere in the image is about 295, right? 296. So I'm going to go back to my dumbbell image. Here it is. And I'm going to do something called image math. I'm going to subtract the dark image from my dumbbell nebula. Subtract. So the operation, the math operation, these are digital images, I'm going to do is to subtract. What am I going to subtract? The dark image. So remember, in my dumbbell nebula, the background was in the 400s. In my dark image, it was around 300, right? Around 295 or so. So if I subtract an image where the background is around 300 from an image where the background is around 430, I'm going to get a new image. And what do you think the background's going to be? We'll find out. So this image is now the dumbbell nebula with that dark subtracted, and now 400 was 450 minus about 300 is about 150, right? So the background is now the dumbbell image minus the dark image. And so I need to set that background now, new background, low brightness limit at 140. There it is back again, and it's a little better quality. It's hard to tell because it was not the greatest quality that night. But you could do the same thing for the 3 other images. Dumbbell nebula green minus dark, dumbbell nebula red minus dark, and then add those 3 dark subtracted images, and that would be an even better quality dumbbell nebula than the one I just showed you. So kind of a long route to optimizing, but there's a lot of extended astrophotography skills that students can develop to optimize their images, because the images are, remember, the images are just numbers, right? And so all the background here is now in the 140s rather than that noisy 400 background image. And that makes your images better. All right. Are there questions about any of the things that I've been showing you? Have you guys been successful at getting RGB images? You can you can unmute yourselves too if you want to just ask my voice. I've overwhelmed you with advanced JS9 features. Okay. Well, if you want to try and review any of these, or you want to try them out and you aren't quite sure how it worked, or you want to implement something new when you work with your students next, I want you to remember that we have office hours with Erica and with Harry. And the office hours are at these times Eastern time. We've noticed people in different time zones looking at the office hours on the YouthAstroNet portal and forgetting that it's Eastern time. So I want to make sure when you see these times, and the link to those office hours is right on the educators portal. If we go here, you can see these office hours are here coming up this week. And when you click on that, you also get a link to the Zoom for meeting up with Erica or Harry. Okay. All right. If any of you would like to type in the chat box, what are some things you want to know about? We'll do our next MicroObservatory Monday to feature that. So if there's any questions you guys have, any particular kinds of things you were hoping students would learn more about, or things you want to investigate, let us know.
Always post it on the portal.
Yeah, and you can always post it on the portal, right? So feel free to use the, you have a, let's see, announcements from the YouthAstroNet team. Right here, discussion forum threads. Questions about the YouthAstroNet activity portal, technical questions about MicroObservatory. Feel free to use these forums to ask questions, and we will answer them. So if you're looking to implement again, please be in touch with Erica about setting up a brand new account for your next group of kids. We are still in the data collecting period, so I'm afraid we're still asking you to get parental permissions for students who are participating. But as we mentioned in last month's webinar, the data we are getting is really showing the power of students being able to use these tools and it promoting student STEM identity. All right, we're going to end this webinar for today. And thanks everybody for joining us. Bye.